Okay, guys. So I am sorry that I can't be there today, but we need to go over all of these 4.5 problems anyways. So I figured I would do a video. And then toward the end, I have some with the answers on here, and I'm going to ask you to do those on your own. You have the answers, so obviously I'm not just trying to get that. I want you to understand how to perform the problem. Okay, so that's what your grade will be on. Did you do the proper steps to get there? And there are a few different ways to do problems like this. I'm just going to show you the way that I saw it. So I always start by just reading my problem. It says, according to the equation above, how many moles of potassium chlorate? So as soon as I have something that has a question like that, I'm going to stop and go back up to my equation if there is one. If there's not one, I'll make one. Okay, but since there is an equation, I'm going to go right in that I'm looking for moles of this substance so that I don't get confused with what I'm looking for. Also, I'm sorry that this got cut off. We're not going to worry about that for a moment. Must be decomposed to generate 1.0 liters of oxygen gas. So that tells me something else. I have 1 liter of oxygen gas, so I'm going to go over here and put 1.0 liters so that I know that that's what I'm given. And then if you notice, it also says standard temperature and pressure. So anytime you see standard temperature and pressure, that means that you can go ahead and write that 1 mole of this gas is going to equal 22.4 liters of the gas, okay? So then we just want to get started with what we know. We're going to start with whatever our given is. We only have one given in this situation, so we're obviously going to start with 1.0 liters of O2. And always remember where you're trying to go. You want to go from moles of O2. You want to go from O2 to moles of potassium chlorate. But in order to transfer through the equation from one substance to another substance, you have to be in moles. So the first step is going to be to go from liters to moles so that we can then do a mole-to-mole conversion of oxygen to potassium chlorate. So back down here to my given. So I'm just going to go ahead and make my equation bar. You don't have to think about it too hard right now. You have liters of oxygen, so you don't want liters of oxygen. So you're going to drop that, and then you're going to think, what type of conversion factor, do I know about liters? Well, because this is standard temperature and pressure, we know that we can use this conversion right here. That 22.4 liters of oxygen is going to be equal to 1 mole of oxygen. That then cancels out your liters, and I'm at moles of oxygen. Well, what did I tell you we can do when we get to moles? When we get to moles, we can do a transfer of one substance to another using the coefficients in the equation. And if the equation is not given for you, you would have to create one, okay? So, undo. We need to continue because we are not at our goal. We do not stop until we get to moles of potassium chlorate. So you're just going to drop what you have because you don't want moles of oxygen, so you're going to drop it. Well, then you rethink right here. What conversion factor do I know with moles of oxygen that can get me closer to moles of potassium chlorate? Well, I know, according to the equation, that for every 3 moles of oxygen formed, it took 2 moles of potassium chlorate. So then that cancels out my moles of oxygen, and I'm left with moles of potassium chlorate, which is my goal, which means I will stop and I will solve the problem. Okay, when I solve the problem, I'm going to need my calculator, so give me 1 second. And you're just going to say 1 mole, or 1 times 1 times 2. Obviously, that's just 2. That was just me doing the top right here, multiplying across the top. And then I will divide that by the entire bottom of 22.4 times 3. So 22.4 times 3. I made sure to put that in parentheses. And I get 134.4 moles. If you check your answers, this is number 5. Number 5 on your sheet did not even give you, I didn't have to solve this far. It was a bunch of fractions and stuff. So let me go and show you the answers and we can look at that together. So on the answers, you see right here that I just have a bunch of these fractions. So if you notice, the only thing they did is they just took all of the numbers out and then put moles beside it. This is the only one that we did. We took 1 times 1 times 2, and we also divided that by 3 times 22.4. So this is the only one that matches our factor labeling right here. Okay, now I did a lot of extra steps just to make sure that y'all understand how to factor label and that you're like refreshed on all of those little bitty steps, because it's the little steps that make the big problems a lot easier. Okay, let's look at number 6. Okay, number 6 is a 20.0 milliliter sample of the 2.2 molar potassium carbonate. Now, I will say that we already worked this one in class and we got pretty far, but we didn't finish it. So I'm just going to jump ahead to where we were at that point. So I think we made the equation first. I'm probably going to have to move this down so that we have more space. Okay, so the first thing we did was make our equation where we have K2CO3 plus BaNO3, and then we're making a barium carbonate precipitant. So barium carbonate plus potassium nitrate. And we talked about how you make these 1-to-1 ratios right here. Barium is a +2 and carbonate's a -2, so you don't need to have more bariums or more carbonates. Same thing here. Some of you had forgotten that that's how we make our compounds. Please don't forget that very crucial step, because if you do forget, you will not have a balanced equation, okay? So in order to balance this, I'm going to put a 2 right in front of the potassium nitrate. Now, the only thing that solidifies is the barium carbonate. Everything else is an aqueous solution. So the question itself is asking us for the concentration. Sorry. Oh my gosh, I cannot pick the right one. The concentration, and again, what are units of concentration? These are moles per liter. So I'm going to need a volume, and I'm going to need moles of the barium ions because it specifically wants it of barium ions. So that does not mean that we are trying to solve for the barium carbonate, because that's not a barium ion, okay? What we want to do is figure out which one of the two givens, this one or this one, is your limiting reactant. And then once we figure out which one's your limiting, we want to know how much excess barium you're going to need. But if you notice, we're going to have barium nitrate as the excess. So you don't have to do the math. I did the math for you in class, but we don't have to do it, because if we're going to find the concentration of barium ions, that must mean that the barium nitrate is our excess reactant because there's extra barium left over. But I could prove that to you. We're going to start with each of our givens. Typically, I would write it on the equation, but I didn't give myself enough room. So I'm just going to start with the potassium carbonate one, where I have 20 milliliters, but 20 milliliters is the same thing as 0.2 liters, 0.02 liters, I'm sorry, because you need to move the decimal 3 times. So 0.02 liters of K2CO3, and I'm trying to get to moles, and you can just pick what you want moles to be in. Well, I'll do this one, why not? Because we don't want to be tempted with the barium carbonate solid, so we'll just solve for moles of this so that we can compare how many moles of the potassium nitrate this one makes, and then how many moles of the potassium nitrate the barium nitrate makes, so that we can see which one makes the least, and therefore is the limiting reactant. Okay, sorry, that was a lot of words. So I don't want liters, so I'm going to drop it. And then I'm going to think, what conversion factor do I have with liters? Well, I do know that I have I have a lot of stuff up here. I just need to get rid of some of it. I know that I have a 0.2 molar concentration of the potassium nitrate, and molar is moles over liter. So I know that 1 liter contains 0.2 moles of potassium 2 carbonate. Okay, Now that I'm in moles, I can transfer through the equation. That was my plan. The liters have canceled, and I don't want moles of potassium carbonate. I would like to do moles of potassium nitrate. Again, you could have solved for either of the two products. I just chose this one because why not? Because all we're trying to do right now is compare how much the potassium carbonate makes versus how much the barium nitrate makes of the same product. Okay, so when I put this in my calculator, I'm doing 0.02 times 0.2 times 2, and then I'm dividing that by 1, which is just 0.008. Okay, I'm going to do the same concept, but this time starting with the barium nitrate. So I'm going to say 0.03 liters of barium nitrate will make how many moles of potassium nitrate. So I don't want those liters, so I'm going to drop them. And according to the concentration right here of 0.4, every 1 liter contains 0.4 moles of that barium nitrate. Okay, I have finished my liters. Now I'm in moles of barium nitrate, which means I can then transfer 2 moles of potassium nitrate as planned. So mole of BaNO3, 2. I have every one of these will make 2 moles of the potassium nitrate. I'm getting these numbers from the balanced equation above. So if you did not balance your equation right, notice how this would not be correct. Okay, so I'm going to work out this 0.03 times 0.4 times 2 divided by 1 gives me, I don't feel like I got that the first time, hold on. Gives me 0.024. So as you can tell, and we already knew this based off of the wording of the problem, but your potassium nitrate, you formed less potassium nitrate from this 0.2 molar potassium carbonate. So this one right here would be your limiting reactant, meaning that your barium is in excess. We would like to know, the whole problem right now is wanting to know how much excess. So I'll tell you what I'll do. You can start with different things. You can start with your limiting reactant and solve for how much of that barium you have left over. Or you can start with this number right here that you just found. To me, that's just a faster route. So I'm going to start with 0.008 moles of potassium nitrate. And I'm going to solve for moles of just barium because that's what I'm looking for. Remember right here when we wrote down our goal. Okay, so I'm in moles of potassium nitrate. I would like to go to moles of just barium. So before I can do that, I need to get to moles of barium nitrate because I can go from this compound to this compound based off of the equation. So for every 2 moles of potassium nitrate, you make, you used 1 mole of barium nitrate. Okay, so now that I'm in moles of barium nitrate, I can switch over to moles of barium because remember this is an aqueous solution, so the barium nitrate is not actually together. So for every 1 mole of barium nitrate, there's also 1 mole of barium ions. So 0.008 times 1 times 1 and then divided by 2, that was not hard math, I get 0.004 moles of barium, and this was what was used. Ooh, that's a problem, right? Because that fact that it's used means that we don't have what's left. So we need to figure out how many moles of barium did we originally have. Man, this is getting long. Sorry, I just want to move this number 7. Okay, so let's see how many moles of barium we originally had. 0.03 liters of barium nitrate. I had 1 liter of barium nitrate that contained 0.4 moles of barium nitrate. It's a 1-to-1 of barium nitrate to just the barium ions. Oops, I don't know why I did an arrow right there. I'm sure there are many different ways of doing this, a lot easier ways. I just get stuck on a route and I just kind of go that way. If I weren't explaining it to you right now, it really would go a lot faster. But still, this is a long problem, so it probably is going to take you a minute. So this is how much was used. So, oh wait, not used. That's how much we had. So if you subtract 0.012 moles minus 0.004 moles that was used, you get, I don't trust my ability to subtract, so y'all just, I know, you probably already know the answer, but 0.008 moles of barium ion. Now, remember I wanted concentration, so you now need to divide this by the amount of liters in solution. The two solutions were added together, and it was 20 milliliters and 30 milliliters according to the original problem. So that makes 50 milliliters, which is 0.05 liters. So when you divide these two right here, you get 0.16 molarity concentration. And then if you look at number 6, the answer was 0.160 molar of barium. Okay, I'm so sorry that was so long. I hope that you followed. There are a few different routes that we could have taken. We did not have to do this in yellow or this right here because according to the problem, we had barium left over. So we already knew that the limiting reactant was the potassium nitrate. You could have just started right here, okay? But I just wanted to prove it to you just in case you didn't believe me, I guess. Okay, let's do the next one. I need to move some of these down. They're going to get all messed up. Okay, so number 7. Aren't we glad we have a fresh page? Number 7, a mixture of gases containing 0.2 moles of sulfur dioxide. So I'm going to go ahead and put this right here, 0.2 moles, and 0.2 moles of oxygen. So before I even get started, I'm going to notice that there are 2 givens right here. So that is probably leading to some type of limiting reactant problem. But we're just going to keep reading just to make sure. In a 4-liter flask reacts to form the sodium, oh my gosh, SO3. Why can't I remember? It's sulfur. If the temperature is 25 degrees and the pressure of the flask, what is the pressure of the flask after the reaction is complete? So since it is complete, that means that all of that is transferred over to the SO3. So this is kind of a multi-step one here because we need to figure out the moles to get the pressure because we know that it's PV equals NERT. Let's go back and look at the answers of this problem though so that you can see how it's written. So the answers of the problem are kind of sort of written in a PV equals NERT concept, and none of them actually have any solved answer. So we are going to go back and just remember that, but continue to work our problem as if we're seeing it for the first time and that we don't have any other information. Okay, so we have 2 givens, which means we need to figure out which one is the limiting reactant. So we're just going to take both and solve for how many moles of SO3 they both can make. So I have 0.2 moles of SO2, mole of SO2. I know that 2 of these creates 2 of the SO3s. So I'm going to create 0.2 moles of the SO3 in that situation. For the oxygen, I have 0.2 moles of oxygen, and I know that 1 mole of oxygen makes 2 moles of the SO3. So that will give me 0.4 moles of the SO3, indicating that this one is in fact the limiting reactant. So this is the N that we're going to work with in our PV equals nRT. Okay, that was not necessary. I say again, because if you're pretty good at this, you would realize that this 2 to 2 is going to be your limiting instead of a 1 to 2, because for every 2 of these, you make 2 of these, whereas every 1 of these, you make 2 of the other. So it's, you could have figured it out by there, but I like to do math just to check. And if you're fast at it, it really doesn't waste too much time. But okay, back to our problem. PV equals nRT. And we would like to solve for pressure. So let's rearrange this where we have pressure by itself. So we're going to get rid of the volume and say PV equals nRT over V. So the N is 0.2. The R is 0.08. I don't know. It's in your answer key. Hold on, I have it right in front of me. 0.08206, okay? And then 25 degrees Celsius, 25 plus 273, you get 298, sorry, over the volume of 4 liters. If you go back and check your answer options, the only one that matches would be this one. Notice that they didn't use the 0.08206, but they all do that. So that's not a problem that you have to worry about. Pause. I forgot a key thing. Notice this 0.3. I forgot something. It's all of the gas in the container. And if you have, this is a limiting reactant, this is an excess. You have more oxygen that did not fully react because this is a limiting reactant problem. So I am so sorry. I'm going to have to back up. So what we know is that the SO2 was your limiting reactant. I'm going to erase this so I have more room. So we're going to take that 0.2 moles of SO2 and figure out how many moles of oxygen do we actually use. So for every 2 moles of SO2, you use 1 mole of oxygen. So 0.2 times 1 divided by 2 is just 0.1, right? Yeah. That's how much oxygen we used, which means you started with 0.2 moles of oxygen and you've used 0.1 mole of oxygen. You still have 0.1 mole of oxygen that is left, okay? So this is what you have in your flask along with that 0.2 moles of the SO3. So together, this makes 0.3 moles of gas, which is the N for the PV equals nRT. You do the same thing where you divide both sides by V, and you get 0.3 instead of 0.2 on that mole. So I'm so sorry I forgot that part. Okay, number 8. And then our number 9 is already in the way. Okay, so number 8, when a student adds 30 mils of 1 molar hydrochloric acid, so I have 30, let's change color so it doesn't get mixed up. 30 milliliters of a 1 molar hydrochloric acid to 0.56 grams of iron. A reaction occurs in the following equation above. When the reaction is complete at 273 K and 1 atmosphere, you should notice that this right here is STP, which means you can use 1 mole of gas is equal to 22.4 liters. Which of the following is true? Okay, when I did this one, I think I went all around the world trying to figure out which of these answers match up with the whole limiting and excess. So if you don't know that D is correct, so let's white that out so that we can pretend that we don't know that, okay? Then you don't know what you're solving for. You don't know if you're solving for the iron chloride or the hydrogen, so you have to pick. I think I chose iron chloride. Let me see. Yeah, I chose to solve for iron chloride. It did kind of make my life a little harder once I realized that that wasn't the answer, but we're going to do it anyways. Okay, so we have two givens right here and right here. That means that this is a limiting reactant problem. And limiting reactant problems, you pick, if you're not told which one, you pick a product and you solve both of the problems towards that same product so that you can compare. And I choose to do moles so that I don't have to go any further. So I'm going to solve, I'm going to take the 0.56 grams of iron and I'm going to solve for moles of iron chloride. So I have grams of iron, so I'm going to drop grams of iron. And I'm going to solve for moles of iron using the molar mass. And I've already done it, and it's, let me find it, 55.8 or roughly 56. And then once I'm in moles, remember once you're in moles, you can do that direct transfer through the equation right there. So I have moles of iron. For every 1 mole of iron, I get 1 mole of iron chloride. And this is just 56 divided by 56 pretty much. Or 0.56 divided by 56, which gives you 0.01 moles of iron chloride formed. And it really is 0.00. The reason I took it further is because one of the options is 0.015. And you notice that that is not the answer based off of the iron. And that's, we can't make more than 0.01. So automatically C cannot be the correct answer. Okay, let's solve using the hydrochloric. I'll switch to purple. So for the hydrochloric, I want a moles of iron chloride, which is a 1 unit. So I'm going to start with the 0.03 liters of hydrochloric and say 1 liter is equal to 1 mole according to the 1 molar. Now that I'm in moles of hydrochloric, that's when I can transfer over to moles of iron chloride. It takes 2 moles of hydrochloric to make 1 mole of iron chloride. So when you do that math, you end up with 0.015, which could be very tempting for C, because notice that that is the number that you got. But can you actually make 0.015 moles of iron chloride if you don't have enough of the iron to begin with? You cannot, okay? So this is the max amount of iron chloride that you can make. So C is not an option. Let's look at the other options. Hydrochloric is in excess, and it is. Hydrochloric is in excess. Yes, hydrochloric is the excess of this. And then it says 0.1 mole of hydrochloric remains unreacted, and 0.02 moles of hydrochloric remains unreacted. Okay, so if you want to be tempted by those, you can figure out how much you've used and then subtract it. You also have this option down here, which we know is correct because we already had the answer key, of 0.22 liters of hydrogen gas has been produced. So you just pick where you want to go with this. I'm going to go with the one I know is the right direction for time's sake. So I know that my limiting reactant is 0.56 grams of iron. So I'm going to take that and solve for liters of H2 just to see if I get the right amount. So drop the grams, 50, we'll just say 56, it's close enough. Gives me 1 mole of iron. And now that I'm in moles, I can do the transfer through the equation. 1 mole of iron also makes 1 mole of hydrogen. And then remember that since this is at STP, we can use this right here. 1 mole of the hydrogen to H2 gas is 22.4 liters. So when you solve this, you do get that 0.22. You actually get 0.224, but according to all of the sig fig rules and stuff, we're going to stop there. And just because that's the only answer choice available. So I got to an answer choice that is correct. So I stopped. I also knew that one was correct, but I just didn't really want to have to go solve for amount of hydrochloric that was used and then have to do my subtraction. So I just did that one instead. Okay, number 9. Reaction 2 occurs with an excess of 6. Okay, so hold on. Let's talk about all three of these reactions. So we have, I like to kind of glance at them and see what's happening. You start with calcium carbide and you react it with water. This was the exploding pumpkin, by the way. I just missaid that, but exploding pumpkin. And you get your acetylene gas and your calcium hydroxide. We stopped there. Reaction 2, you take sodium and OCl, I don't actually know what that's called, react it with hydrochloric and you get chlorine gas and sodium carbide and water. And then we have acetylene gas plus the chlorine gas and you get whatever the name for that is. Okay, so reaction 2 occurs with an excess amount of hydrochloric acid, okay, of 6 molar. And is added to 100 mils of of unknown concentration. If the reaction goes to completion and 0.01 moles of chlorine is produced, then what was the molarity of the NaOCl? All right, so let me figure out where I started with this because okay, so reaction 2, we have a lot of givens here. We have 6 molar hydrochloric. We have 100 mils of this. So we can automatically, that right here, just by looking at it, I have the liters part of the concentration because I want molarity. I just need the moles, 0.1 liter. I just need moles of the sodium NaOCl. And I know that it goes to completion to create this amount of chlorine gas. So I'm going to start here so that I can then take this moles and go backwards to get the moles of the NaOCl. So 0.01 moles of Cl2. I'm automatically at that mole. So that's really convenient that I can just go, okay, this is a 1-to-1 ratio. But they are balanced because they did put numbers in. You always have to check for that. Sometimes they don't balance those equations. So this is a 1-to-1. So 1 mole of chlorine comes from 1 mole of NaOCl. So that means that we have 0.01 moles of the NaOCl. So now that you know the moles, you can put it into your molarity equation right there. Say 0.01 moles is divided by 0.1 liters, and you get 0.10 molarity for that NaOCl. And that was answer choice C. Okay, so here's what we're going to do next. I have the answers to all of these. I'll pause and let you, you can stop the screen and look at them and solve the problem on your paper. You have the answers, so you should continue to work until you get to the right answer. But what you're going to do is you're going to write these problems on a piece of paper, write all of it, okay? And then you are going to solve, and I'm going to look at your work to solve, okay? You should be able to get to the answers that are written. Okay, if there's any questions, you can infer with each other, you can talk with each other, but I don't want you to just copy each other's work down because you're not actually going to learn or get anywhere from that. I don't think any of these are different than what we've already done, but these notes are also going to be uploaded on Canvas, so if you need to write these down, not from the video, you have that as well. But I will be back on a Tuesday to answer any questions that you have.